Okay, in today's class, we are going to talk about linear design models. So now here is the basic idea. So everything starts with those 12 differential equations of motion. Those 12 differential equations of motion are nonlinear and coupled. And you have done the task already. You got those 12 differential equations of motion, you program those, you specify certain forces, certain moments, and they generate the appropriate solution, and you are using that solution to fly your UAV. Now, what we want to do in chapter 4, we studied forces and moments that are acting on that UAV. So the next part of the assignment is we are going to calculate the aerodynamic forces, propeller forces, and feed those forces Fx, Fy, Fz, and I think Lmn torques to the forces to that equation. Now, what's going to happen is, in addition to those forces and moments, we have controllers. What type of controllers do we have? We have aileron, we have rudder, and we have elevator. Whenever we deflect a control surface, the behavior of the aircraft changes. So whenever we deflect a control surface, the behavior of the aircraft changes. What causes this change in the behavior? And I want you to understand it. Deflection of control surfaces is equivalent to modulating external forces and moments. So in your differential equations, you have Fx, Fy, Fz, L, M, and N. 3 forces, 3 moments. With 3 control surfaces, ailerons, elevator, and rudder, you are going to manipulate these forces and moments. And as a roboticist, our job is to manipulate those forces and moments so that the aircraft performs the maneuver that we want. That maneuver could be a level flight. That is also called as trimming. Now, I want you to understand, whenever an aircraft flies, aircraft will never fly horizontal. Aircraft will always fly at certain angle. If a helicopter flies, helicopter cannot fly at level angle. Helicopter cannot fly like this. Helicopter will always fly like this. And the reason for that is the rotor of the helicopter needs to produce forward thrust so that the helicopter can move forward. So these are the 2 different flight characteristics of these 2 different vehicles. So when you start working on a tilt rotor, which takes off as a helicopter and then flips into airplane mode, these 2 flight modes need to be incorporated in the mathematical model of the aircraft. And what you do is you change the forces and the moments by the control surfaces. Sometimes what you do is you change the speed of the prop. That changes the thrust on the aircraft, and you control the aircraft motion. As you know, those equations are very complex and those equations are very nonlinear. So these are the equations that we are going to deal with. And in these equations, the only thing here is, remember, all the aerodynamic forces have been included as Fx, Fy, Fz, and then L, M, and N. So what I want you to note that these super complicated looking equations, this stands for F of X, this stands for F of Y, and this stands for F of Z. And then you will notice again, what we want to do is these forces f of x, f of y, and f of z are dependent on the control surfaces. Once again, the control surface that controls the aircraft motion in the pitch plane is called as elevator. The control surface that controls the aircraft motion along the roll direction is aileron, and the control surface that controls the aircraft motion about z is called as rudder. So what I want you to do is, I want you to carefully follow. Here you have delta E, here you have delta R, delta A, and here you have delta E. So what that means is you have these different types of control surfaces. Delta E stands for the deflection of the elevator. Delta A stands for the deflection of the aileron, and delta R stands for the deflection of the rudder. So as you can see that you have all these equations wherever those control surfaces are popping in. In addition to that, you have something called as the motor thrust. So delta T stands for the thrust. Now, similarly, if you carefully follow these equations, which are for P, Q, and R, you will also observe that thrust is coming in the picture, aileron is coming in the picture, rudder is coming in the picture, elevator is coming in the picture, aileron is coming in the picture, and rudder is coming into the picture. So what I have shown over here, these are the control surfaces that the pilot or the autopilot has a control on. So remember, this is what is going to happen. These equations, they look super complicated, but in these equations, we have control over delta E, delta T, delta R. And what we are going to do is, somehow we are going to manipulate those delta E, delta R, delta A, and delta T. We are going to manipulate these parameters so that we get the desired behavior from this aircraft. That desired behavior could be a level flight. Aircraft flies steadily. The desired behavior could be aircraft turns, which is called as coordinated turn. Aircraft will never turn like this. Okay, aircraft will never turn like this. If aircraft has to turn, aircraft will always turn like this. So that is called as the coordinated turn, because it's like a coordinated turn. And coordinated turn is very important for passenger comfort. So whenever you see aircraft banking, if the turn is not coordinated, as a passenger, you will feel it. As a passenger sitting in the plane, you will feel the sideways push. So what we are going to do is, at the end of the day, even though these equations are complex, no matter what your flight vehicle is, your equations are going to have similar form. In those equations, you are going to have 12 equations. In 12 equations, you are going to have 3 forces and 3 moments. You can manipulate those 3 forces, 3 moments, and thrust using the control variable, which is the physical deflection of the control surfaces and changing the speed of the prop. Everyone understood this? So now in this chapter deals with something called as the linear design models. So you see this super complicated equation, this super complicated nonlinear equation, we are going to linearize, which means we are going to make it into as simple as 1 burger for $1, 2 burger for $2. So we are going to convert this super complicated equation into very simple linear equations that we can realistically solve. Why do we need to do this jugglery? Please understand, this is for two reasons. Even though these equations or these functions are non-linear, but in a very small operating region, those can be approximated as a straight line. So even though the behavior, these differential equations are complicated and non-linear, you can, if you take a very small snapshot of the trajectory around the operating point, you will notice that the behavior is linear. What it means is there is a simplified representation of these equations that we can realistically solve. And if your flight regimen is non-complex, what do I mean by non-complex? For an example, level flight. If the aircraft is in a level flight, or if aircraft is in a simple coordinated term, or if the aircraft is sort of loitering, these are very simple maneuvers, because if you were to take a very simple snapshot, all the states will behave linearly. So what we are going to do is we are going to take these super complicated nonlinear equations of motion, approximate these equations into some linear form, and use those linear functions to control our dummy aircraft. And believe it or not, this technique works quite well. As a matter of fact, even if you have a complicated equation, even if you have a complicated aircraft, you will notice that in majority of the flight regimen, final equations, they assume this linearized form. Let me tell you, we will observe that when we try to linearize, some terms are nasty. We cannot get rid of those. Those nonlinear terms are going to remain. But what we would do is we will treat those nonlinear terms as disturbances, and somehow we would cancel it. Everyone understood this? So what's going to happen is we'll try to simplify these equations and then come up with a very simple equation like mx double dot plus kx is equal to f of t, something like this. A very simple linear equation. But there will be some nonlinear part that would remain that we will treat as a disturbance. Now, what is this disturbance? This disturbance is all this nonlinearity that making this model super complex. But we will design our linear controller so that linear controller is able to compensate for that small nonlinear disturbance. Everyone understood this? And that is the principle behind gain scheduling. So when we do the quadcopter control, we will notice that these techniques can be used. Again, these equations look scary. And once I show you the next page, they would look scary here because the terms in here, they have some terms. So for an example, if I expand these, as you can see, there are these terms like gamma 3, gamma 4, and all these terms. They have their own expansions. But as an engineer, you don't have to worry about these. There is a data file that when you simulate the data file, just like Aerosonde or just like Zagi, that data file will contain all this information that you download in your program and run it. So every aircraft, we are not aeronautical engineers. We don't deal with how to calculate. We have to do wind tunnel testing and all to find out these values. But as a roboticist, these values will be given to us. And what we would do is we'll use these values in our simulation. Everyone understood this? There are two types of motions we are going to consider. One is a longitudinal behavior, and then the lateral behavior. So we will study the longitudinal behavior of the aircraft and the lateral behavior of the aircraft. As soon as those 12 sets of equations are linearized then what you can do is you can simply use the Laplace transform or state space, or you can use a pole placement, or these simple techniques in linear control to control the behavior of that complex system. And once we have confidence in whatever system, the system we have that works, then we can go a step further and then try to play with the nonlinear equations. If the aircraft is like F-16, which is a very complicated maneuvering aircraft, or if the aircraft is unstable in nature, you cannot use linear or linearized equations, and you will have to use the original nonlinear equations. So we will look at that. This is something that we talked about in last class. Usually we don't do it in simulation, but if you want to include the effect of stall, which means something like this: aircraft is flying, aircraft is pitching, aircraft pitches, and after certain pitch, it actually falls down, because aircraft can no longer generate the lift because there is a flow separation on the wing. Aircraft goes forward, pitch, all of a sudden, aircraft like flips down. So basically that's drag. If you want to include the effect of drag in level flight or in regular operating region, you don't have to worry about it. But if you want to include the effect of drag, then what you do is you add this something called as the blending factor, and then you combine these two equations so you can approximate the behavior of the aircraft near stall. Okay, that's where you can approximate the behavior of the aircraft near stall. But for normal operation, you don't have to worry about it. And these equations we looked at in last class. So right now, what we have is all these complicated equations. Once I approximate that as a linear model, please note this equation is as simple as y is equal to mx plus c, where x is alpha. So I have this equation wherein I have the coefficient of lift and I have angle of alpha. So in the operating region, I can just say that as my alpha increases, my coefficient of lift increases. As my coefficient of lift increases, area remains the same, then my total lift force is going to increase for constant airspeed. Everyone understood this? Now, we are going to do something which is called as trimming. And we are not going to do trimming by hand. We will use MATLAB to perform the trimming. What is the meaning of trimming? I don't know. Have you flown RC quadcopters, RC plane? There is a function which is called as trimming. What does that trimming do? Trimming would adjust the control surfaces so that the aircraft is in level flight. Now, what do I mean by aircraft in a level flight? For every aircraft, the definition of level flight could be different. For an example, if you have a fixed wing aircraft, level flight means aircraft is flying at a constant speed at a certain angle of attack. So aircraft is flying at constant speed at certain angle of attack. But as aircraft is flying, realize that there are aerodynamic forces, there is gravity, and there are thrust forces. So all the forces are balanced in such a way that the aircraft continues to move. Now, please understand, trimming is similar to stability, but stability is typically a static stability, which means all the forces are zero, all the moments are zero, all the velocities, all the accelerations are zero. Please understand, on an aircraft, if all the forces, all the moments, all the velocities, all the accelerations are zero, that aircraft will become a rock. You don't want that. We want that aircraft to continue to fly in a level flight, which means the aircraft must achieve the dynamic equilibrium where the aircraft is moving at steady velocity. Everyone understood this? That is the meaning of trimming. For quadcopter, trimming means the quadcopter is able to hold its altitude, or quadcopter is able to hold its position, not rotate about the yaw axis. That is why the trimming is done in quadcopters. But in the context of the aircraft, what's going to happen is we want the aircraft to continue to be in steady flight. So basically, we will make sure that the control surfaces are adjusted such that all the forces are balanced, all the moments are balanced, except the forward force or forward thrust. And we'll look at those variables as we go through the formulation. Now, I want to talk about this important maneuver. Remember, aircraft has roll and yaw coupling, which means if you were to yaw the aircraft, aircraft is going to roll. Aircraft cannot yaw something like this. Aircraft cannot go like this. If the aircraft has to yaw, it is going to roll. So as you can see on the left hand side, you have you see an aircraft which is yawing or which is turning. But because the aircraft is turning, you can see that it's rolling. As the aircraft is turning, it is rolling. Now, what we want is we want the centrifugal forces acting on the aircraft to be balanced. We want the centrifugal forces on the aircraft to be balanced. We want the gravity or the weight of the aircraft that is acting, that needs to be balanced. So what we do is, in the yaw domain, we write this equation: lift force and the phi component of it, lift force, and the roll component of it. This is the component of lift in the plane which is going down, and this has to be equal to the centrifugal force. Centrifugal force. And then what you do is, as you can see, which is m r omega square, and which r omega is nothing but v. So this equation got written at m times v times omega. This is r times omega. V square by r is omega square r square, and then basically you get this equation, which is nothing but m multiplied by va, which is the airspeed multiplied by the yaw rate. So this is the mass of the aircraft. This is the airspeed. And this is yaw rate. And then if you want to look at the component of lift, which is in the plane of the gravity or in the plane of in around jk, I'm sorry, around kb, you have F lift cosine phi, that is equal to mg. And then what you do is you perform a simplification wherein you get F lift from the left hand side, substitute that over here, and you get this equation, which is given as psi dot is equal to g divided by va tan phi. Now, you have experienced this equation. Let me tell you, when you fly in an aircraft, you have experienced this equation. What does this mean? This is the yaw rate. If the aircraft is yawing at certain rate, whether you like it or you don't like it, for that particular airspeed, there is an angle, roll angle phi that the aircraft will attain. So which means that's why when the aircraft are yawing, you don't yaw the aircraft very fast. You actually do a slow yaw. So yaw rate, if you specify, so pilot decides the yaw rate. G is gravitational acceleration, VA is the airspeed. For this condition to be valid, the aircraft will attain an equilibrium for tan phi. It will maintain a non-zero phi, and then the aircraft will turn. Everyone understood this? If you fly in an aircraft, I guarantee you have experienced this. Okay, the previous in this problem, this is an ideal case. There is no wind. Remember, we talked about the ground speed is equal to the air speed plus wind speed. Ground speed is as if the aircraft would have been on ground. What would be its speed? The ground speed is equal to the air speed. That means the speed at which the aircraft is flying with respect to the surrounding air, and the wind speed that could be aiding or that could be sort of resisting. So this is the equation when there is no wind. However, if there is wind, then this equation becomes a little bit complex. And what I want you to see here is you get this angle chi, and then basically you subtract your heading angle. So as you can see that you will, if you have wind, so what does wind do? Think about it, that aircraft wants to go in this direction. If you have wind, that wind is going to change the relative heading of the aircraft. If the aircraft wants to go like this, but the wind is coming like this, the effect of wind will be to sort of yaw the aircraft more. If the wind is acting in the opposite direction, then basically the effect of aircraft, the effect of wind to rotate the aircraft towards that direction. So basically, this term, what you are seeing is because of the wind. And then once you actually solve that equation, which is something similar to the equation that we have seen earlier, and we have seen this triangle quite a few times. And remember this is a very important relation. So you have this VA. So you have this VA. So VA, which is the airspeed, this is airspeed. This is wind speed. That is equal to ground speed. So this is the relation that this is, and we looked at it. This is called as the wind triangle. Now, one important thing is aircrafts do not have speedometers, okay? Because the wheel speed does not give you a relationship how fast the aircraft is going. What aircrafts have is they have something called as the pitot static tube. So if you look at any aircraft, typically at the nose on the left-hand side, you will see a small pipe extending out, a small pipe extending out. That is called as the pitot static tube. There are two ports. There is one port which is the absolute pressure, and the second port measures the differential pressure. What it does, there is actually a manometric fluid, and the difference in the manometric fluid gives an indication of how fast or how slow the aircraft is going with respect to surrounding air. Now, typically in the helicopter, what you do is, if you look at Apache helicopters, in front of Apache helicopters, there is a strong, this long pipe, small, long pipe that comes out of Apache helicopter. That is used to measure the airspeed. So that's a pipe. It has two holes, and you can measure the absolute pressure and the relative pressure. And that gives you, using Bernoulli's principle, you can find out the speed of the upcoming airstream. So coordinated turn is an important maneuver. Now, in the next phase, again, what happens is, finally, at the end of the day, you will land up with an expression that we have seen earlier. So if you look at the previous equation, divide both the terms. Please understand, we have this equation when there is no wind, and I want you to notice that when there is no wind, the heading angle is the course angle. Heading angle is equal to psi, and that gives you this. This is called as chi. And so if you have wind, then you get this equation. This is the expression with wind. So these are the two expressions. And then the turning radius is, again, turning radius is just like the cornering radius for a car. If you have a car with small wheelbase, you can turn it quickly. If you have a car with large wheelbase, you will need a larger radius. Something similar to that, the aircraft has a turning radius. So Boeing 747 has a larger turning radius compared to Cessna. So, and those equations, those turning radii are dependent on the airframe, and they are dependent on the airspeed, and they are dependent on the value of heading angle or heading rate. So these two expressions are very important. Now, next part, which I want to spend some time on talking about, is this trimming. We are going to do trimming when we integrate force and moment blocks with respect to the differential equation block, and that is differential equation block sending out information to the flight. So I want you to understand, trim condition is also considered as an equilibrium condition. Equilibrium state. Now there are two types of equilibrium. One is called as the static equilibrium, and the other one is called as the dynamic equilibrium. Now I want to give you an example of what I mean by static equilibrium. Imagine you have a pendulum, something like this, okay? And the length of the pendulum can vary. Think about it like it's a rope, and then you have a bob at the end, and the length of the pendulum can vary. Now what you do is, you basically perturb the static position, which means you give that bob a little push, and what's going to happen is this bob can actually go forward, backward, and it will continue to do so in vacuum. But if this mass or this bob is in the air would add damping, and eventually after some time this mass will come to a rest. So basically that the whole thing will dampen out, and then all the forces will be zero, all the moments will be zero, all the velocities will be zero, and this thing will be in static equilibrium. Summation of forces is equal to zero, summation of moment is equal to zero, or accelerations and all velocities are zero. Everyone understood this? That is called as the static equilibrium. Now what I want you to do is, I want you to imagine same bob, but I start rotating like this. And at certain speed, what's going to happen is, at certain speed, you have the centripetal force and you have tension in the string that will balance each other so that it actually continues to rotate in this dynamic equilibrium. So this is called as the dynamic equilibrium or trimming. So it's an equilibrium, which means the things are steady state, but things are not zero. So things are in steady state, but things are in not zero. So trim is also called as steady state and then there is a concept which is called as the stability around trim. And I want you to understand this concept very, very carefully because that is what we are studying in the aircraft stability. Now, imagine I have a very simple pendulum. And this simple pendulum is hinged at this point. And again, the length is fixed, the mass is fixed, length is fixed, and the mass is fixed. And on this pendulum, there is a motor, and that motor is giving a sinusoidal torque. So what that means is this pendulum, just like your grandfather clock, is going back and forth, back and forth, back and forth. Okay. And there is a small amount of torque that is going clockwise, counterclockwise, clockwise, counterclockwise. And that grandfather clock pendulum is swinging. It is in steady state. Now, what happens if when this pendulum is in the steady state? So pendulum is going back and forth, back and forth. And what I do is I disturb that motion, that steady state motion. So what I do is, this is the grandfather clock, and I kind of tap it. And I kind of tap it. There are two things that can happen. First, that grandfather clock pendulum can basically become unstable. It will go something like this. Or if the magnitude of the perturbation or the magnitude of external disturbance is small, then what will happen is it will like go a little bit outside, but finally it will come back to its original equilibrium position, dynamic equilibrium position. Everyone understood this? And this simple example is super important. I'll give you an example again, because I want to talk about the nonlinearity, approximating nonlinearity as disturbance. So please try to understand. I have this pendulum that is swinging, and then what I do is I perturb it. But the torque that I have, as you can see, that torque is linear. That torque is proportional to angle. So torque is linear. So torque is like going back and forth. Even though my perturbation is nonlinear or creating some disturbance, as long as my linear torque is able to overcome the disturbance, even though the nonlinear disturbance is nonlinear, my linear control will work. Everyone understood this? So once again, let me tell you. So for an example, I have this pendulum, and then what I have is I have this torque, and then I disturb it. But my torque is sufficient to overcome the disturbance and put that pendulum back into its equilibrium or trim position. What that means is my linear model is able to control the behavior of the pendulum. Everyone understood this? And that is going to be the key assumption when we talk about the behavior of an aircraft. So what I want to tell you is there is a stability about equilibrium state, and there is stability about the steady state or a periodic solution. For an example, if your solution is periodic, this is the steady state behavior, and all of a sudden, if there is a disturbance, then what should happen is, as time goes on, that disturbance should die down, and it will continue to go on to the steady state. Everyone understood this? This is exactly the type of behavior we are trying to achieve in our aircraft dynamics. In our aircraft dynamics, aircraft is not stationary, because aircraft stationary can be only on ground. Aircraft is flying, but during flight, there could be a disturbance. This disturbance will be a nonlinear function of the vehicle states, or could be the nonlinear function of external air velocities or anything. There will be a disturbance. but the linear control surfaces will provide enough force and enough torque so that they can overcome this nonlinear disturbance and make this aircraft fly in a level flight. Everyone understood this? That is the goal of this development. Trimming condition means aircraft should be able to stay in a level flight. Then we are going to change the controller algorithm so that even if there is a disturbance, aircraft goes back to its trimming position. Everyone understood this? Because some of these concepts are going to be little. How do we find out trimming? Again, there are different techniques. For a simple equation, it's very easy to find the trimming state or a periodic solution. But when you have a super complicated nonlinear expression involving 12 states, you have to use some type of numerical technique. And that you use something like a numerical optimization. So what I want you to do is, I want you to understand that calculation of trim means calculation of the aircraft parameters, specifically calculation of aircraft control surfaces deflection around certain flight regimes. So these flight regimes are traveling at the constant speed, climbing at the constant flight path angle. Flight path angle is the aircraft angle with respect to the ground. So basically flying in a constant flight path angle and in a constant orbit of radius. Aircraft turning. So these are the flight conditions that we are going to use to find out the trimming. You cannot calculate the trim when aircraft is doing a sudden motion. You can only calculate the trim or the steady state when the aircraft is in steady state. So these are the steady states. Traveling speed at constant speed, climbing at constant path angle, and in constant orbit radius of r. Now what that means is VA star, gamma star, which is the flight path angle, and R star are the input to the trimming conditions. So basically, what we are going to do is, in those 12 equations, we are going to find out certain values of delta R, delta A, and delta E, and delta T, so that VA, gamma, and R, these remain constant. Everyone understood this? Now, some of you may ask me, then how do we do that? Clearly, it's impossible to do that by hand, unless the flight regime is a simple level flight and you make certain assumptions. So what we are going to do is, this is what we are going to achieve. Remember, our differential equations have 12 states. What are those states? North position, east position, down position. This is height or altitude. Forwards velocity in x direction, velocity in y direction, velocity in z direction. We have the role which is rotation about x, rotation about y, and the rotation about z. And then we have P, Q, R. These are the rates, angular velocities or angular rates about x, angular rate about y, angular rate about z. Everyone understood? No Newtonian here, just Euler angles. Everyone understood this? As a pilot or a flight control, I have control over 4 parameters. Elevator deflection. What does elevator control? The pitch. Then I have aileron that controls roll. I have rudder that controls yaw, and I have thrust that controls the forward speed, essentially the airspeed. So delta E, delta A, delta R, and delta T. These are the surfaces, or these are the parameters that have control on. Everyone understood this? So what I'm going to do is I'm going to define few flight states. So for an example, if again, if I have a constant climb orbit, then what I have is U star, V star, and W star is equal to 0. And these are the dots. What it means, so U, V, and W are the angular velocities. Angular acceleration about X, angular acceleration about Y, and angular acceleration about Z is equal to 0. Everyone understood this? That is going to be my state. How does this condition reflect into this equation? What I'm going to do is, I'm going to take the derivative of angular acceleration, a derivative of angular velocity, and equate that to 0, which means this guy will be 0, this guy u dot, v dot, and w dot, right? So the accelerations in x direction, acceleration in y direction, and acceleration in z direction will be 0. Okay, just let me confirm quickly. Yeah, u dot, v dot. So these are accelerations in x, acceleration in x, acceleration in y, acceleration in z. These are linear accelerations. So u dot is equal to 0, v dot is equal to 0, w dot is equal to 0, which means this equation gets equated to 0, this equation gets equated to 0, and this equation gets equated to 0. Everyone understood this? Are you with me so far? So u dot is equal to 0, v dot is equal to 0, and w dot is equal to 0. Now, roll and pitch angle are constant, which means what you have is, you have these values, which is the roll, pitch, and then P is the angular acceleration about x. So P dot is angular acceleration about x. Q is angular acceleration about y. About y. They are treated 0, which means what I'm going to do is, I will go back to this equation, and then I will say theta dot is equal to 0. Then P dot is equal to 0 and Q dot is equal to 0. So P dot is equal to 0 and Q dot is equal to 0. Are you with me so far? So as soon as I'm trying to find out trim mathematically, what that means is this term has gone to 0, 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 and this term has gone to 0. That is the first thing that we need to do. Now, second thing, what we want to do is, now we need to specify some type of a constraint, and turn rate, which is psi dot, is V8 divided by R, which is the radius of turning, and then we have this gamma angle that is specified. So this is the constraint, which is the turn rate is constant, that yields R star, which is R dot is equal to 0, which means that gives me the angular acceleration about z, acceleration about z is equal to 0. So if I want turn rate constant, then this equation becomes 0. Now, as you can see, as soon as I set, this is extremely important. As soon as I set the derivative term equal to 0, now I have got a set of equations. Those are differential algebraic equations, which means I have some terms. They have algebraic relationship, a plus b is equal to c. And I have some terms where there are dots floating around. Everyone understood this? As soon as I try to find out trimming, what I do is I actually make these derivatives is equal to 0. So I get an equation which is an algebraic equation, and I have some equations which are differential equations. So finally, what we got is we got a differential algebraic system. If my climb rate is constant, then I have this additional constraint h dot star. Now, what does this mean? H dot star means the aircraft is continuously climbing. The altitude is changing. So as you can see, that is h is the height. It is nothing but PD. PD dot is h dot. Now, what my software or what my program should do is, given bunch of zeros, given this condition, I want to find out the values of Pn dot, P dot, H dot, U dot, V dot, W dot, all these values. So what I want to do is, given these constraints and given these bunch of equations that are differential equations and algebraic equations, I want to find out these terms. So this is what it means. If you want to find out the trim or the steady state, which means remember those 12 equations. In those 12 equations, the left-hand side of equation 1, 2, 3, 4, 5, 6, 7, 8. Left-hand side of those 8 equations will be equated to 0. And then you have this equation, because that is indicating the yaw rate. And this is indicating the climb. This is yaw rate. And then please understand, first two terms, which is Pn dot and Pe dot, because Pn dot is the forward acceleration and Pe dot is east acceleration. We are okay with whatever we get. Okay, so basically, the trimming means you take those 12 equations, set some equation is equal to 0, set some equations is equal to constant, and finally find a solution that satisfies left-hand side is equal to right-hand side. Everyone understood this? You got these 12 equations. Trimming means you are going to make some terms on the left-hand side 0, some terms on the left-hand side is equal to constant, and then try to find out the values of the variables so that the left-hand side is equal to right-hand side. Everyone understood this? Now, please understand, we are dealing with a very complicated nonlinear equation, which means it may be possible that we can find one trim position, we can find 2 or more trim positions, or there would be no trim positions, because it's a nonlinear equation. It can have 0 solutions, multiple solutions, or one solution. So how do we do this? Again, yeah.
Weren't we not first linearizing them and then solving?
Yeah, you can do linearization and solve it. That is one way to go. But since we have MATLAB that can do trimming on these complicated equations, why not to basically trim them in the first go? But okay, let me tell you. The way linearization works and I was joking, okay, so the way linearization works is linearization is valid about an operating point. So what I mean by that is if you have a sine wave, if you have a sine wave, if you have a sine wave, if you linearize over here, you have a straight line. But the expression you get for this straight line is not going to be the same. That is the expression for this straight line. What it means is your linearization is, or the Taylor series expansion is dependent on the operating point. The Taylor series expansion is dependent on the operating point. That's why the first step is finding out what is that operating point. So idea is first we do this trimming to find the operating point, and then we do the linearization about that operating point. Everyone understood this? Remember, Taylor series expansion is not valid everywhere. I want to give you an example. Sine theta is equal to theta. Remember, yeah.
So from a practical standpoint, does this mean that we have to, if we're running a control loop like 100 hertz, we have to recalculate the trim position of the vehicle constantly as
Yes.
speeds and position changes?
Yes. So basically, I just want to give you an example. Remember, sine theta is equal to theta. We have used this assumption all the time since we are in high school. What does that actually mean? Which means if you substitute sine 17 degrees, then you will notice whatever magnitude you get is similar to the value of 17 radians. You will see here the left hand side is equal to right hand side. So please understand this expansion or this assumption that a nonlinear function is expressed as a linear function is valid as long as the theta value is greater than 17 degrees. What does that mean? Actually speaking, which means you have the 0. Now, if you go positive 17 or you go negative 17, you have a straight line expression. But if you go 20, 25, 30, 35, 40, 45, this assumption is not valid because you will have to find the linearization about the operating point that you are linearizing. Everyone understood this? So first and foremost, find out the trimming or the point or operating point, and then linearize so that your model will be good. And there is a rich nonlinear theory behind it. So there is something called as, it's not given in the textbook, something called as the Hartman-Grobman theorem or Grobman-Hartman theorem. What that states is the stability of nonlinear system is similar to the stability of the linear system as long as the eigenvalues have negative or positive real parts. What does that mean? It means if you have this complicated nonlinear equation, you have this complicated nonlinear equation or nonlinear dynamical system, and you want to understand whether that system is stable or unstable, then what you do is you find the operating point, you find the linearization, and find the eigenvalues of the linearized system. Remember, nonlinear systems do not have eigenvalues. Linear systems do. So you find the eigenvalues of the linearized system. If the eigenvalues have negative real part or positive real part, you can confidently say that the nonlinear system is stable or unstable. Yes.
But if eigenvalues are positive, wouldn't that mean that pole is on the right hand side?
Yeah, so it becomes unstable. What it means is linear system is unstable, your nonlinear system is going to be unstable. Now here is the trick around it. So what you do is you design a controller and I want you to, this is the crux of linear control theory. This is the crux of nonlinear control theory. To design a controller so that you push those eigenvalues, you make them so negative, or you make those make those that system so stable that even if there is nonlinearity, the system poles do not cross the imaginary plane. Everyone understood this? That is the crux of linear control theory. That is the crux of pole placement. In a sense, you will. So when I went to industry, when I was working on Bell 609 flight controls, I was very passionate. My PhD was in nonlinear dynamics. So I was like, yeah, let's use the nonlinear techniques and try to do the nonlinear analysis and control. Then when I looked at the actual control loops, they were linear. And then I asked the question to the flight engineer, why these loops are linear? He said that even the system is nonlinear, but if you are performing the linearization trimming at 1,000 times a second, that teeny tiny time window, which is called, they call it as frame. In that frame, the system behaves linearly. So even you may have a system which is nonlinear, but you are looking at a so teeny tiny snapshot of the trajectory, state trajectory, that you can linearize it. The only difference is depending upon the operating region, this linear model will be good or that linear model will be good. So what you do is you design controllers depending upon those different linear models. And that is called as the gain scheduling. You have a different gain when the aircraft is at this operating region. You have a different gain when the aircraft is in other operating region. That's all to it, the gain scheduling. Then my next question was, why are we using PID controls? And you will realize, we'll see here that we are going to use simple PID controls. As a matter of fact, if you look at Pickhawk, which is the professional flight controller, it also uses PID controls. Then I asked, why are we using PID controls? The reason we use PID controls, because they are easier to implement. They are easier to understand. They don't have divide by zero type of singularity. If you use an exotic nonlinear control, you can get a very good journal paper out of it. Maybe you can show its implementation on few cases, but you cannot prove that it will work all the time unless you use some type of a Lyapunov or global control theory, because nonlinear controls are typically local controls. So you cannot. So even if you want to use it, FAA will not allow it, because you have to prove that anything that goes on the aircraft, whether it's a hardware, whether it's a software, whether it's a piece of code, whether it's a piece of bracket, you have triple redundancy. So which means one system fails, you have other system fails, you have third system. You have to show, you have to prove, and you have to actually, there are test protocols as per DO stand and MIL standards. You have to actually perform the testing and prove to FAA DER that your system is triple redundant. Otherwise, the FAA will not allow you to fly. And actually, that is why, if you notice, over last 50 years, we haven't seen many aircraft accidents. And before 1930s, 1950s, there used to be a lot of aircraft accidents because the aircrafts were not safe. But because of these FAA regulations, because of these standards, because of these test protocols, the airplanes or air flight or air travel has become safer. As a matter of fact, every aircraft, every Boeing 747 actually stripped down at the end of 8 years of service, or depending upon the flight hours. Whether the airframe is good or bad doesn't matter. That part will be replaced. And that's why the aircrafts are very expensive. And that's why we have a company, if you see across next to airport, which is Able Engineering. That's what they do. When the aircraft original parts get replaced, the original parts gets refurbished, which means it is actually treated, tested, and made sure that part is as good as new. It has to be as good as new. Only then that part can go back onto the aircraft. So there are, so the industry, by the way, Able Engineering is hiring if you are interested in applying. And our students graduated from here are at leadership positions at Able Engineering. So please apply. So then, so we got this differential algebraic system, which is a complicated equation. And if you take an optimization class, basically the class taught by Professor Jang or class taught by Professor Chattopadhyay, which on optimization, all that class deals with, you got these constraints, you got these expressions, and how do I find out the solution? How do I find out the value of the variable that satisfy the equation and the constraint? That is all there to it for optimization. So you have equations, you have constraints, you have equations, you have constraints, and then basically how do you find out the optimal solution? And then there is something called as unconstrained optimization, which means you don't have any conditions. Unconstrained means free floating. You don't have any conditions. It needs to be optimized. At the end of the day, let me give you a simple example. You know the basics of optimization. Take the first derivative, equate that to 0. That is the crux of optimization. Unconstrained optimization, which means equate is equal, so take the derivative, equate it to 0, and find x, but you don't have any restriction on x. Constrained optimization means take the derivative, x dot is equal to 0, find the value of x, x is equal to c, x dot is equal to 0, x is equal to c. That c has to be within certain region. Everyone understood this? That is constrained optimization. You can make it as complex as you want. You can change, you can make a multivariable of optimization. Instead of x, there is x1, y1, z1, x2, y2, z2, and so on. You can make it stochastic. X1s varying with some randomness. You can make it your external conditions, instead of having a constraint, constant constraint, you have a variable constraint. You have a dynamic constraint. So you have a dynamical system. So at the end of the day, remember optimization, x dot is equal to 0. If you specify the limits on x, that is constrained optimization. If x is limitless, that is unconstrained optimization. Everyone understood this? That's what we are doing. But optimization problem are extremely difficult to solve by hand. If someone says, oh, I'm going to optimize and I'm going to use scratch paper and find optimization, not possible. You have to use numerical techniques or computer algebra or MATLAB or R or Python to find that optimal solution. So you have something called as the unconstrained optimization, and then you have something called as the constrained optimization, which means you're restricting in the region. And again, you can have a constraint that is x needs to be between 0 and 5. So you can have a constraint which is an inequality constraint, or you can have an equality constraint, which means x can only be 1 or 2, or x can be in between 0 to 5. X can be between 0 to 5 is inequality constraint, and x can only be 1 or 2, that is an equality constraint. And these constraints will get written in a different mathematical terms. So what you're seeing is the mathematical way of writing these constraints: equality constraint and inequality constraint. And then we will use all this physical intuition to actually look at the lateral transfer function. Let me tell you, this may look scary, but this is extremely simple. This may look scary, but what we are going to do is we are going to take the scary part, combine it together, and call it a disturbance and cancel it. So what we are left with is a very nice good looking, well behaving part. And we will do that in next class. Okay, I'm gonna stop here.